going to look at some trig integrals now, primarily when we have powers of cosine and sine. So one of the things we're going to start with, we're going to look at this example here, and you notice that it's got a power of 3. We're going to use our Pythagorean identities to help us split this up and to use substitution to find the integral. So I've split it up so cos squared x times cos of x. Now, using the identity of sine squared of x plus cos squared of x equals to 1, we can rearrange this for cos squared of x. So cos squared of x is going to equal 1 minus your sine squared of x. If we substitute that in, we get 1 minus sine squared of x times by your cos of x. Now we're going to look at using substitution to actually evaluate the integral. If we let our u be sine x, our du is going to be equal to cos x dx, which is exactly what we have here. So we have the integral then of 1 minus u squared du, which isn't hard to figure out. The integral of 1 is going to just become u, and then the integral of negative u squared is going to become minus u cubed over 3 plus c. Then we substitute back in our u as sine of x. So as a result, we'll have sine of x minus sine cubed x over 3 plus c. There also are some reduction formulas that will help us with this. Because you have powers of n, we just looked at one example with a power of 3, you can see there's somewhat of a pattern. When we get into higher powers, we're going to have multiple ways we can split up using the Pythagorean theorem. So this pattern falls for all sine and cosine functions that have a power of n. The first term will be 1 over n, negative in the case of the sine, positive in the case of the cos. Of sine, and you drop the degree down by 1, multiplied by cos of x. Here we drop the degree down by 1 and multiply by sine of x. Then we add the integral, and we drop the degree down by 1 over the actual degree, and then we take the integral of the degree of the sine dropped down by 2. In this case, the cosine of 2. So here's an example where we have sine to the 5th degree of x. And if you notice here, I've just followed the formula. I've written out it already, so you can see negative 1 over 5. My n is 5, so I plug 5 down here. I drop the degree of the sine to degree of 4, so I do 5 minus 1 to get sine x to the 4th of x, multiplied by cos x, plus, and here we drop the, sorry, the 4 over 5 is your n minus 1, so your degree of 5 minus 1 all over 5, and the integral, we drop the degree of the sine down to degree of 3 over of x. Now if you notice here, we can actually evaluate this again by using again the same sort of method. So the next one, we will keep our negative 1 over 5 sine to the 4 of x times cos of x plus 4 over 5, and then we have to do this whole thing again for this integral right here. So with the degree 3, our n now becomes 3 and 3. So we have negative 1 over 3 sine. 3 then drops down to 2, so 3 minus 1, so 2x cos of x plus n minus 1, so 2 over 3. And the integral, and now we drop down our sine by 2, so we have just sine of x dx. Now if you notice here again, we distribute our 4/5, but we still have another integral of sine x dx that we have to evaluate. So we can now write this as negative 1 over 5 sine to the 4th of x cos x plus, or I should say minus here, because it's multiplied by a negative, minus 4 over 15 sine squared x cos x, and then we'd have plus 8 over 15, and the integral of sine x dx becomes negative cos x. So let's change this to a negative cos x plus c. Another good example to look at is the integral of tan x dx. Now, we do also know the integral of tan x dx can also be written as the integral of sine x over cos x dx, mainly because tan is equal to sine over cos. Now, if we use u substitution, we can then evaluate this. If we let our u be equal to cos of x, the derivative of u is going to become negative sine x dx. So then you can rewrite this integral as negative integral 1 over u, which is our cos, du. We also know that the integral of 1 over u is going to equal negative ln of u plus c. Now, because we know our u is cos, we can then insert cos, so ln cos of x plus c. We also know that when we have a negative or a number outside of a log or ln, we can use that as an exponent. So a negative 1 exponent means that we're actually going to have ln of, and I guess it's 1 over your cosine of x. The absolute value really only needs to go around the cosine because one absolute value is 1. So now we have this, and we know that 1 over cos is the same thing as going secant of x plus c. So another one of the identities that they showcase is that the integral of tan of x dx is equal to the ln of secant of x plus c. So in the textbook on page 423, there is a table of all the trig integrals that you might want to take a look at. This will be provided to you, but you do obviously need to know how to use them. And you need to know how to apply them when you now have instances such as integral of, let's say, cosecant squared of something. Again, we're going to look at how to use u substitution along with all the identities that we have now for cosecant squared dx. So things like that you need to look at. I would suggest spending a little bit of time and looking at some of the identities for trig that you need to know, such as the Pythagorean identity, sine squared of x plus cos squared of x is equal to 1. That's one identity that's very useful. The double angle identity is also very useful. If you ever have sine 2x, we know that's equal to 2 sine x cos x, as well as a double angle identity for cosine. So cos 2x is equal to cos squared x minus sine squared x. Those are also useful when you're doing any sort of simplification. And I think that's about it. So those are some key ones that you'll want to look at, as well as the table that is on page 423.